In Chapter 3, we're going to learn two topics of importance when studying organic reactions. The first one is over resonance, which you would have heard about resonance in general chemistry, but we're going to look at it in a whole new way. And then the second topic that we're going to cover is acid-base chemistry. So we're going to review some concepts from general chemistry over acid-base and then learn how to apply them to organic reactions. So before we jump right in and look at resonance structures, I just want to review a little bit of line bond structures and formal charges. When you look at a line bond structure, it's important that you can figure out the formal charge if you are given all of the lone pairs of electrons and vice versa. So formal charge is something that we will use to predict stability in a reaction and stability in our molecule. So you want to be in the habit, you must show the formal charges when you draw a molecule. So if we look at this example here, when you see this line bond structure, yes, you want to know where the carbons are and you want to know how many hydrogens are coming off of a carbon, but notice all of the lone pairs of electrons are shown. This is not normally the case where every single lone pair is drawn. Organic chemists are lazy and they want to take the shorthand method, which is just showing formal charges instead of always having to put lone pairs on each of the atoms. So when I look at this, I want to hone in right away and be able to identify what atoms would have a formal charge and what they are. So right away, the oxygen on the far left, I can see that that oxygen has 3 bonds to it, a double bond and a single bond. So that represents 3 electrons. And then there's a lone pair, which is 2 more. So it has 5 around it total when it would like 6. So this oxygen has a +1 formal charge. So I would throw that positive in there. The oxygen on the top right, that has 7 electrons around it. So right away I would see that and I would know that that oxygen has a -1 formal charge. This oxygen right here has a 0 formal charge. You don't have to write 0 if that's the formal charge. We just don't show anything. So we only show the formal charge if it has a difference than 0, anything different than 0. The other one that I see right away is the nitrogen on the right-hand side. That has 4 single bonds, so that means 4 electrons around it, and it would like 5, so that nitrogen has a +1 formal charge. So you're not going to show lone pairs of electrons, but you are always going to show formal charges. And you should be able to work backwards and figure out how many lone pairs something has if you're given the formal charge, or you should be able to figure out the formal charge if you were given the electrons for some reason. Specifically, we're going to focus on carbon atoms that have a formal charge. So first, we're going to look at carbon atoms that have a positive formal charge called carbocations. Usually, carbon will try to have 4 covalent bonds in order to have no formal charge associated with it. But sometimes you'll see carbon that has a +1 charge. In this case, the carbon will only have 3 bonds to it, and this is what is referred to as a carbocation. Cation because it has a positive charge. When we look at the structure of carbocations, what could we say about them? Why might they be unstable when compared with a carbon atom that is bonded to 4 things? So if we look at the first one on the left, that carbon in the center, that carbocation, is only bonded to 3 things, 3 other carbons in this case. So there's no hydrogen coming off of that carbon, which is why it is a carbocation, because the formal charge is +1. So it only has 3 bonds to it, not 4. When we look at the second one, that carbocation has a carbon, and then how many hydrogens are not being shown? Well, if it's just a carbocation with a +1 charge, there must be 1 hydrogen coming off of there that's not being shown. So when you look at a carbocation, you should still be able to figure out how many unshown hydrogens there are in the line bond structure. And then on the last one, you've got your carbocation, and that's bonded to 1 carbon. So that would mean that unshown are 2 hydrogens coming off there. So in each case, this is a carbocation with a +1 charge. You won't see a carbocation form where it has a +2 charge. That's just even more unstable than a carbocation with a +1 charge is. So why is this unstable in the first place? Well, what is the valency of carbon there? Does it have a complete octet? And the answer is no, it does not have a complete octet. There's 2 electrons here, 2 here, and 2 here. So this carbocation only has 6 valence electrons. And so carbocations, they're usually highly reactive. They're not stable. Your carbon does not have a complete octet. And so they are an important intermediate that we'll learn about when studying mechanisms. The other type of structure that you could see where carbon has a formal charge is referred to as a carb anion. And just like it says anion, that means carbon would have a negative charge. And at most, the carbon will have a -1 charge. So just like we saw with the carbocation, at most, the carbon developed a +1 charge. So carb anions, you'll notice that there's a lone pair of electrons on the carbon. And so when we look at the formal charge, if we were to break those in half, we have 1, 2, 3, and then 2 more from the lone pair, so 5 total electrons around carbon. It likes to have 4, so hence it has a -1 formal charge. Just like our carbocations, carb anions are not the most stable either, compared to when carbon has no formal charge and has 4 covalent bonds to it. And this is mostly due to the fact that carbon is not very electronegative. There are many more atoms that are much more electronegative than carbon, and they would much rather bear a negative charge rather than something like carbon. That negative charge on that carbon is not in a great orbital either. Carbon is sp3 hybridized. And so something we'll learn is you can figure out the percent character of S compared to P in a hybrid orbital. And the higher the percentage of S character is, the more stable those lone pairs would be because they would lie closer to the nucleus. But in this case, it's only about 25% S character. And so it's just not a great hybrid orbital for that negative charge to be lying in. So carb anions are unstable as well. At the end of the day, if you have a carbon that does have a formal charge, you must show that formal charge on the carb anion or the carb cation. As I said previously, when you look at line bond structures, the lone pairs are usually omitted. They're not shown. So when we look at a structure like that, on the nitrogen, it's not showing any formal charge, and we know that lone pairs are not usually shown. So if you don't include the formal charge, how do we know exactly how many electrons there are on that nitrogen atom in a structure like this? It's just a question mark for now. It could be any one of these 3 structures that we see below. Nitrogen could have 2 lone pairs and have a -1 formal charge. Does nitrogen contain 1 lone pair and have a +1 formal charge? Or is nitrogen a radical, where a radical has 1 unpaired electron, and those are highly unstable molecules. So that's why it's really important that you always draw the formal charge, and that will eliminate any source of confusion, since that is the standard rather than showing lone pairs of electrons, which can get messy to look at. When we're looking at a structure, the lone pairs are not shown, so we want to work backwards from them to figure out what the formal charge on a specific atom is. So below, how many lone pairs are on the oxygen atom that are not being shown? We know that oxygen has a -1 formal charge, and that is what's indicated. So when you see a molecule like this, you want to get in the habit of training your brain to instantly think about how many lone pairs must be there. So when we look at this, we know that oxygen normally has 6 electrons around it. We would have to subtract 7, and that would give us -1. So we must be able to have 7 electrons around our oxygen atom. One of those electrons is going to come from half of the bonding, so that one right there. The other 6 would be 3 lone pairs around our oxygen atom. So 3 lone pairs of electrons on that oxygen atom. Something that helps you quickly determine the number of lone pairs on a given atom is by knowing its bonding pattern. And this just comes with a little bit of practice and kind of seeing a lot of molecules over and over again. For example, when you see an oxygen atom that has 1 bond, that means it has 3 lone pairs around it. So just like in that example that we saw on the previous slide, oxygen with one bond to it is equivalent to 3 lone pairs every time. And that oxygen will always have a -1 formal charge when it's like that. When oxygen has no formal charge or a 0 formal charge, that means it has 2 bonds. What's not being shown is that there's 2 lone pairs. So in this example, oxygen is bonded to an ethyl group, and it's also bonded to a hydrogen. So it has 2 bonds, and what's not shown is there's those 2 lone pairs on the oxygen. So when we see this molecule on the left, we know it's equivalent to this molecule on the right. But we know that there's those 2 lone pairs because the oxygen has no formal charge and it's a divalent molecule, meaning it likes to form 2 bonds. And the last bonding pattern that you'll see for oxygen is when it has 3 bonds to it. When oxygen has 3 bonds to it, that means it has 1 lone pair on it that's not shown, and that has a +1 formal charge. So in our example, we have a propyl group bonded to our oxygen. That oxygen is also bonded to 2 hydrogens, and it has a +1 formal charge on it. So what's not being shown on the structure on the left-hand side is that lone pair, that single lone pair on oxygen. But what is always shown is that +1 formal charge right next to the oxygen when it's following this bonding pattern. So an example of this would be something like the hydronium ion, where oxygen is bonded to 3 hydrogens, and we saw that hydronium had a +1 formal charge. Well, that +1 charge is really on the oxygen. Just like oxygen has certain bonding patterns, so does nitrogen. Oxygen and nitrogen are 2 other atoms in addition to carbon to kind of be really familiar with. When you see them, you know exactly how many electrons are not being shown there, and you can quickly look at something and identify if it has a formal charge on it. So one of the bonding patterns for nitrogen is when it has 2 bonds to it. What's not being shown is it has 2 lone pairs on it, and that nitrogen will have a -1 formal charge. So our example is shown below. We have our nitrogen that's bonded to a carbon and to a hydrogen. We show a -1 right by that nitrogen, indicating the -1 formal charge. What's not being shown is that nitrogen has those 2 lone pairs there. So it actually has 6 electrons around it instead of 5, which is why it has that -1 formal charge. Nitrogen is trivalent, so it likes to form 3 bonds, and when it does, it'll have no formal charge or a formal charge of 0. So when you see 3 bonds, what's not being shown is that it has 1 lone pair on it. In our example below, nitrogen is bonded to a carbon and to 2 hydrogens. So we've got a propyl group, nitrogen, and then 2 hydrogens. If you want to show it the long way, by writing NH2, that's just kind of the shorthand method for the molecule I drew below, where I show the 2 covalent bonds to nitrogen and hydrogen. What you are not seeing in the structure on the left is that lone pair on nitrogen that you have to understand is there. Because if it's 0 formal charge, it must have 5 electrons around it. 2 from the lone pair, 3 from half of the covalent bonds. And the last bonding pattern for nitrogen to be familiar with is when it has 4 bonds and it has no lone pairs on it. Then nitrogen will have a +1 formal charge. So an example is something like ammonium ion or derivatives of the ammonium ion. So nitrogen, if you look at half of its covalent bonds here, it's got 1, 2, 3, 4 electrons around it, and it likes to have 5, so that nitrogen has a +1 formal charge. No lone pairs are on nitrogen when it has 4 covalent bonds to it.